Again, welcome to data structure class. This is CS 435 class. In this lectures, we're going to cover the concept of graphs. So our main objective again is to learn about graphs, become familiar with the basic terminology of graph theory. Also, we're going to discover how to represent graph in computer memory. We're also going to explore the graphs as ADT, which is abstract data types. In our next lectures, we will go through some few algorithms, especially we will go through the shortest path algorithm, also the minimal span tree algorithms, and also various graph transversal algorithms. So first we start with the definition, what is a graph, and also the notations we are going to use in these lectures. So here we said, before we start again, we will go through some few symbols which we normally use in set theory. So here we are going to borrow some few definitions and terminology from set theory. The main goal here again is the symbols. So for example, if we said if element or A is an element of X, then we can write it as A belongs to X, or element A belongs to a set of X. So the symbol here again means belongs to. Now, if we said Y is a subset of X, it means we have a set Y and all the elements in set Y is also in a set X. But there are some elements in set X that may not be in set Y. So Y is the subset of X, and that's the symbol we use for subset. Now, intersection of A and B, and that's the symbol here. This means all the elements in both A and B that are common. So a set of all elements that in A and B. Now the union of A and B, which is the symbol here, A union B, means we are going to get all the elements that are in both set A and B. So the set of all the elements that are in A or B. Then we also have A by B. This reads as we have element A and B such that A belongs to set A and B belongs to set B. Again, the lowercase a is the element, uppercase A is the set. So now we start with the graph definitions and notations. And here we say that a graph G is a pair such that G equal to VE. V represents vertices, E represents our edges. So again, edge will be a line that connects two or more vertices together. We may have a graph with only one vertex. A graph with only one vertex doesn't have no edge. So in order to have an edge, we need to, again, two vertices. So here we say V is a finite, non-empty set of vertices. And again, our symbol here means subset. So edge, the edge E, subset of V by V. This means an edge will connect two vertices, or here called a set of edges. And this is the element of E are the pair of element of V. So E is called a set of edges again. Also, we have G is called the directed graph or digraph if only the elements of E and G are ordered pairs. Otherwise, G is called an undirected graph. And we shall go through. So we have two types of graph here. One is directed and one is undirected. And again, we may discuss this. So we can also say, okay, let V at G donate a set of vertices and E at G donate a set of edges of the graph G. Now, if the element of E at G are ordered pair, this is called a directed graph or digraph. Again, if G is called an undirected graph, it means again, it's not unordered. Again, we shall go through this more detail when we get to the diagram. So here we say if U and V is a digraph or directed graph edge, this means vertex U is called the origin and vertex V is called the destination. Now, undirected graph means I can move from U to V, or we can move from V to U. It's undirected. Directed means if you have U and V, it's only one direction. We go from U to V. We can't go from V to U. And again, the diagram here will give a small example. So all these three graphs are example of undirected graphs. We can see the edges are the lines, and the dots with numbers is the vertex. So here we can see that we can move from 1 to 2. We can also move from 2 to 1. So this is undirected. There's no any specific direction to go through. And these are all three different examples of undirected graphs. Now the difference is here we have directed graph. So let's see G1. With G1, I can move from 1 to 2, but I cannot move from 2 to 1. So this is called a digraph or directed graph. Because again, we can move, for example, from 3 to 4, the direction is given to us. I can't move from 4 to 1. So those are the two types of graph for now. So now we go detailed by the graph definition notation. Here we say adjacent vertices have an edge from one to the other. So what we mean by adjacent vertices, we can go back once. Let's say 1 and 2, they are adjacent vertices because I can move from 1 to 2. But from 1 to 5, they are not adjacent because I cannot move from 1 to 5. But rather I can move from 1 to 2 before 5. So the definition adjacent vertices means they have an edge from one to the other. And we say consequently, the edge is incident on both vertices. Also, we may have the concept of what we call the loops. A loop is an edge incident on a single vertex. So which means the edge will start from one vertex and it will go around and end at the same vertex. And that's called a loop. And again, we will see the diagram soon. Also, we have a parallel edges. Parallel edges are incident on the same pair of vertices. And also a simple graph has no loop and there has no parallel edges. Vertices are connected if they have a path. And with these terminologies, we can see a very good definition. So let's go back to our graph here. In this graph here, we don't have no para and we don't have no loop. A loop means I'll start from vertex 0 and I'll end it at the same vertex 0. A para means I have 0 to 1 and I may have another edge from 1 to 0. And we will see example in a few slides to come. So we also have some few definition. Here we say a connected graph has a path from any vertex to any other vertex. So we go back example in our previous diagram. We have a path from 1 to 5 means I'll go through 1 to 5. Or I can go another path 1, 4, and 5. Or we can go the longest path from 1 to 3, 4, and 5. Again, I'm assuming this graph is undirected. But for now, this graph is a directed graph. That means to get a path from 1 to 5, I have only two options. I can go 1, 2, 5, or 1, 4, 5. I cannot go 1, 3 because 1 and 3 goes to 1. 1 doesn't go to 3 direction. So that's a loop and a para, and also the concept of a path. Vertices are connected if they have a path. Now, a connected graph has a path from any vertex to any other vertex, as we said earlier. Now, the component of G, the goal is to maximize the subset of connected vertices. And again, we may come details on that. G is also strongly connected if any two vertices are connected. G represents the graph. And also if there's an edge from vertex U to V, then U is adjacent to V. And also V is adjacent from U. Again, so far we are covering terminologies and also definitions. So now let's start with the graph representation in a computer system. So first we can represent graph as an adjacency matrix or as a adjacency list. So we start with the adjacency matrix. This is two-dimensional n by n matrix. Now, the size of the matrix would depend on the number of vertices we have in the graph. So if a graph have 4 vertices, then the size of the matrix will be 4 by 4. So here, let's say, let G be a graph with n vertices, where again, n is greater than 0. N is the number of vertices we have. Now, if we have V at G, which is the vertex from 1 to Vn, then the adjacency matrix AG of G is a two-dimensional always, and it will be n by n. Why? Because n is the number of vertices we have. So that is the symbol here, AG, INJ equal to, if it's 1, if only VI and VJ belongs to E at G, otherwise it's 0. So adjacent matrix of undirect graph is symmetric always. Again, we'll see an example soon, but the only thing we should know is the definition. Now, let's say if we have a graph G with n vertices, n should be negative value because vertices, n will be the number of vertices. So we can construct adjacent matrix by n by n. Now with the adjacency list, here we say the corresponding to each vertex V. And I would say let G also be a graph with n vertices. Again, n should be greater than 0. Then we may have V at G from vertex V1, let's say, to Vn. Now in the adjacency list representation, corresponding to each vertex V, there's a linked list such that each node of the linked list contains the vertices U, such that V and U belongs to Y at G. Now, because there are n nodes, we use an array of size n. And that's most important. So because there are n nodes, you can use an array A of size n. Then A at I contains a linked list of the vertices to which VI is adjacent. And the best way to represent this will be the diagram here. So in this diagram is the same as G2 here. So we have the graph G2. So G2, first of all, we can see we have 5 vertices. So our indices from 0 to 4 is 5. This is for adjacency list. Now, 0, we look, this is again a directed graph, so we have to be careful. We are in the vertex 0, and that's the first 0. At vertex 0, we can go from 0 to 1. We can also go from 0 to 3. So at 0, we have the linked list, the 2 nodes, 1 and 3. Then when we go to 1, vertex 1, we can move from 1 to 2, and we can move from 1 to 4. So we have the node for 2 and 4. Now, when we are at 2, we can move to 1, and we can move to 4. So at 2, we have 1 and 4. Now, when we are at 3, we cannot move anywhere. 0 comes to 3, 4 comes to 3. From 3, we don't go anywhere. So we can see at 3, we point to null. Then at 4, we can move only once to 3. 1 comes to 4, 2 comes to 4, but 4 goes to 3. So we have only 3. So this is the concept of, again, representing graph as adjacent list. We can now use a linked list in area. So now we're going to start with the operations on graphs. Again, graph is a data structure, so almost the same operations as any type of data structure. So for example, we can create a graph. we can clear the graph. Clearing the graph means we are deleting all the elements in the graph or all the nodes. Also, we can determine whether the graph is empty. Most important, same as trees, we can traverse the graph. And here we're going to learn two methods in our next lectures, how to traverse a graph, which is the DBF. Again, we'll go through that, and also how to print a graph. So let's start with the implementation. We are going to check if a graph is empty. It will return true or false. Return true if it's empty, false if it's not empty. So we may have this instant variable named gsize. Gsize will keep track of the number of elements we have, or the number of vertices we have in the graph. So anytime we insert a new vertex in the graph, we are going to increment the gsize variable. Anytime we delete a vertex from the graph, again, we are going to decrease the gsize. So if gsize is equal to 0, that means, again, the graph is empty. The next is to create the graph. Again, creating a graph, there are so many ways we can create, how we get our inputs. So in this implementation, we are using the scanner class. So the user is going to enter, again, the input, either using the file system, or in this case, we say system.in. So we're going to get the input from input file. So we have a string for the file name. And now we say that if the size, again, this variable will keep track of number of elements or number of vertices we have in the graph. So here we say if the gsize is not equal to 0, we want to create a graph, because here we want to create a new graph. So we want to make sure there's nothing in the graph. And then we assign node to the infile, the scanner infile. So this infile will be our file handler. So now we go through the steps. First, we ask the user to enter input file name, and console.next line, we get the file name. We print, just to get a space, we print. Then next, we use the scanner class to get a file. So we say new scanner, new file reader, file name, signed to the file handler. Then next, again, we have our catch, and the catch here is against the exception in case we don't find the file is not in the directory that we want to get it. So file not found exception, we print that. If the file exists, then we're going to get a number of vertices. So this is our file handler, the infile.nextInt. We assign to the gsize. Then for index from 0 to index less than gsize, and we increment. So here we assign the item to the vertex. Again, the item will be an integer. So infile.nextInt, we assign to the variable vertex. Then infile.nextInt, we assign to the adjacent vertex. And this will be a loop. So why the adjacent vertex not equal to -99? What we do is that we insert last adjacent vertex into the graph vertex. So until we enter -999, we will stop creating the graph or entry vertices into the graph. So if this loop become true, then we keep entry, creating our graph, enter more vertices. Anytime we enter -999, then we stop. So the while loop stop, and it's control go back to the for loop. So again, that's the implementation to create a graph. Next is to create a graph. To create a graph means we want to make sure there's nothing in the graph. So we use the loop to go through all the items in the graph, because the graph size is gsize And we start from 0, so we have to go to G size minus 1. So index is less than G size. And every vertex we go through, we assign node to it. So we create everything from the graph. And now after we finish, we assign 0 to the G size. So this 0 means, again, we assign 0 to G size means, again, there's nothing in our graph. First, we make sure all the elements in the graph or the vertices, they are known. Then we create. Next is to print graph. So to print a graph, we can use the for loop. It's kind of a concept of array because we have more than one element in the graph. So it's good to use the loop to go through. So we start from beginning up to the end, the G size less by 1. So we have system.out.print, print the index, and then we assign graph index.print. And also at the end, we have system.out. This will print a line for us in order to move to see our reading, our output more clear. Then at the end also we print another line. Now the constructor, here we have a default constructor. So by default, we want to create a graph with a size 100. We make sure G size is 0, there's nothing in the graph. And also we are using unordered linked list. So we have to have this class since we are using linked list now, unordered linked list. So we use the new keyword to create unordered linked list, and the mass size is 100. Now for index from 0 to the less than mass size, we are assigning new unordered linked list, and it's integer to each element or each vertex in the graph, which index start from 0 to the mass size. So again, this is a constructor to initialize and also create our graph. The size will be 100. We are using unordered linked list class and initialize the items to 0. That means we don't have any vertex inside, but it can take up to 100. Then we have the constructor with the size parameters. So this means the mass size can be any size. So previously it's a default constructor. The size is always 100 if we call the default constructor. But this is a constructor, we have to specify the size. So there again, the code is the same. The difference here is that the constructor can be can take any size, 100, 200, 5. So when we call this constructor, it means we need a different size. We can use any size. And also we have the graph transversal. So with the transversal of graph, in this course, we are going to use only 2 methods, which the first will be the depthFirst transversal. This is exactly similar to pre-order transversal binary tree. So when we say a pre-order, it means first we go to, if it's a binary tree, first we go to the node, after which is the root node, then we go to the left subtree, then we go to the right subtree. The same concept here also. So similar to pre-order transversal. Visit the root node first, then go through all the sub left tree, then go to the sub right tree. So here the algorithm says we should mark the node V as a visited. Again, this is a wrong spelling, it should be a visited. Then step 2, we visit the node, which will be again the root. Now for each vertex U adjacent to V, if U is not yet visited, then we start the depthFirst transversal at U. So this should be the depthFirst transversal at U. And this concept is again recursive algorithm. And we may again go through this. So this is the Java implementation for the depthFirst transversal. So it takes argument of V, and also this is an array implementation, so Boolean visited. So here we say, okay, the visited V, if it's true, we assign true to it. Then if that's the case, we print the V. So visit the vectors. As we said, this is pre-order, so always we visit. When we say visit the vectors, means the concept of, again, trace. We visit the root first, then go through all the sub left, then go through all the sub right tree also. So here we have unordered linked lists, and the type is integers. And also linked list iterator, we are using the iterator to go through the items. So here we have the iterator method to go through the graph. Now, why the graph IT, this will be the graph iterator. So graph it.hasness. With iterator, we can use hasness method, hasness check in this next item to go through. So if this condition is true, then we will go to graph it.next. Then we go through the next tree. We assign it to W. Now, if not visited W, then this is recursively, we're going to have W/visited. And that will be, again, recursively going through, again, the vertices. So this is, again, our depthFirst transversal. So we have the Boolean visited. This will be, again, array. The type is Boolean, and this is array to keep track of the visited vertices. So we have the visited equal to new Boolean G size. Now for index 0 and index less than G size, we increment. So we are going from 0 to the end of the items in the, again, the graph. So we assign first, we assign false to visited index. Then secondly, we start from index 0 again, less than G size, increment. That's for each vertex that if not visited index, that if we haven't visit, then we call the DFT to visit through, which is our previous method. Then that will end the depthFirst transversal. So here also we have the DFT at vertex. So we have, again, our Boolean array visited, new Boolean G size. For the loop, starting from 0 again to less than the G size, we assign false to visited index. Then recursively, again, DFT with the vertex and visited. Now with the depthFirst transversal, it's, again, similar to transversing a binary tree level by level, which means, so we saw the depthFirst transversal. It's more or less like pre-order. We go the root, then go through all the left, then go through all the right. It's kind of similar. Here we go through level by level. So the first level, we go through all the nodes. Then second level, we go through all the nodes. So the general algorithm will be for each vertex V in the graph, if V is not visited, then add V to the queue. Then mark it as visited, then you keep going. So it's sequential order, level by level. We go through all the items. So again, this is the implementation. We have the depthFirst transversal. We are using the link queue class to implement it. So we create our queue object. We also have our Boolean array visited. And the visited, we use the new keyword to create it, and the size is G size, the array size. That's the array size. Now, from 0 to less than the G size, we initialize the array visited to false. So we assign false to visited. That's in the index to start from 0. We initialize it. Now, from index 0 to the G size again, less than G size, if we are not yet visited, then our queue object dot, we use the method add queue with the index. Then we assign true to the visited index. Then we can print the index number. Then why not queue dot is empty yet? So here we are checking if the queue is not empty. Again, it's empty queue, check if the queue is empty. If it's not empty, then we assign the queue dot front to you. Then we delete queue. Then we have the unordered linked list. Again, type is integer. And we are using the iterator also. So we are checking using hasNext method to check if we still have an item. If so, then we assign graph iterator to next to W1. Then if W1 not visited, then we add queue to W1, which means we go through W1. Then we assign true to W1, and then we print W1. So this is again the depthFirst transversal. So again, we're going to end the lectures here. The main goal here is the theory aspect of graph. Again, in our next lectures, we may go more detail about the coding concept, transversal, and also we are going to talk about the shortest path algorithm and also the minimum spanning tree also. So again, wish everybody the best. If you have any question, you can send an email or you can post it in the Canvas. Thank you.